So again, a good morning. Today we're going to continue our discussion on the sun. In this case, in this class, we're going to talk about transient solar corona activity. So that includes a very introductory discussion on solar flares and coronal mass ejections, which are the most common transient activities that are happening in the sun. So when you say transient, that means it happens occasionally, okay, with duration of several hours only, no? So very short duration now, no? But before doing that, before discussing this topic, let's have a brief recap of what we've discussed so far. Okay, so last time we talked about the solar atmosphere. So generally, we talked about the surface of the sun, the observable surface of the sun in the visible range. We call that the photosphere, okay, which is described by a decrease in temperature. And then after the minimum temperature, the temperature above the sun increases slightly, okay, until levels of temperature similar to the surface of the sun. And we call that the chromosphere. And then there is a sharp transition region wherein the temperature gradient is very, very steep before it goes to the solar corona. Okay, so we have photosphere, chromosphere, transition zone, and the solar corona. In order to observe the photosphere, we use several wavelengths that are available to us. We use an ultraviolet light continuum, which is seen here. The wavelength of this picture is at 170 nanometers or 1,700 angstroms. This represents the region of the sun of about temperature of about 4,500 Kelvin. Okay, a little over that, about temperature of about a little under that, temperature of about 6,000 Kelvin, we could actually observe the white light continuum. So this is actually the one that is visible to the sun using the visible spectrum, which coincides or matches what is being observed by the Solar Dynamics Observatory using the heliosismic magnetic imager HMI at the absorption line of 617 nanometer. So this is around the red region. Okay, so this corresponds to your iron, the first line in the iron absorption line. Okay, so we usually use the HMI continuum image to visualize where the sunspots or active regions are currently located. Okay, then above that, we can actually observe the chromosphere. It was one of the first ways we could observe the chromosphere is during a solar eclipse, where it appears a red thin line, a very thin layer of red lights at the surface of the sun. That's why it's called the polar sphere. And that red light is actually corresponds, if we're going to take the spectrum of this wavelength of this light, we can actually have traces of hydrogen emission lines. We call this the Balmer series. So this appears red because this corresponds to the 656 spectrum line of your hydrogen emission spectrum. We call that the H alpha. Okay, and if we're going to look at the other spectral lines of this chromosphere, you can actually observe these spectral lines. Okay, aside from that, we can actually observe, because of that, by the way, because of that, we can actually observe the sun in these wavelengths, okay, for the chromosphere. So what does it mean? Okay, if you have a telescope and you place a filter, we call that an H alpha filter. It's commercially available. You can actually observe the emissions of the sun at 656 nanometers, and it would look like this. So this is a picture of the sun using the H alpha spectrum, and you can see the other features that can be seen in the chromosphere. Okay, and similarly, we can actually observe the sun in the 304 angstrom wavelengths. Okay, using the Solar Dynamics Observatory, this temperature the temperature that corresponds to this spectrum is about 5,000 Kelvin. So it's already around a little bit above or near the transition region already. Okay, so if we're going to zoom in, we can actually see several features of the sun. We can see the sunspots, you can see the plages, the filaments, as well as their prominences. Okay, so going above the transition zone, we can actually see the solar corona. So this is the outermost region of the solar atmosphere just before hitting the interplanetary space. Okay, so this region, the solar corona, is actually the interface between the solar atmosphere and the interplanetary space, where solar wind interactions becomes more dominant. Okay, just like before, just like in your chromosphere, we can observe the solar corona via solar eclipse, where can you actually see the coronal structure, which basically corresponds to the magnetic field line configuration of your sun. Okay, so by looking at the sun's corona, we can actually observe or deduce what is the configuration of the solar atmosphere at or solar magnetism, at the very least in the in the view of the limb, around the limb. Okay, of course we cannot actually see the too much about the magnetic field in front and at the back. Okay, aside from that, we can actually produce an image. We call that the corona graph, where in the corona graph is a visualization of the solar corona by inducing a uh, artificial eclipse. Okay, and then we can also see the solar corona at certain wavelengths using the solar dynamics observatory. If we're going to combine the white light corona image from an eclipse and a solar dynamics observatory, specifically in this wavelengths at 193 angstrom, we can actually see several things. Now, first, we can see your helmet streamers. So that is described by wide structure at the bottom near the surface of the sun, and it looks like a cap. That's why it's called the helmet streamers. And this is where some of materials are being ejected from. Okay. Aside from this, at the poles, we can actually observe polar plumes, wherein this is a region of open field lines. This field lines, though it's called open field lines, is actually closed with the interplanetary magnetic field. Okay, and this usually coincides with corona holes. So imagine if you have your window right now. Okay, if you have your window in your room, and then you try to, when you open your window, you can, depending on the situation outside, so sometimes you will feel a gust of wind going into your room. So that's what corona holes do. Okay, so this is actually a window to high speed stream of particles. Okay, which is also uh, can be visualized using the polar plumes. Aside from these three structures, we can actually observe, depending on the solar activity, if there are corona loops, as well as you can actually look at the structure of the solar corona during a quiet, in regions where there is a steady magnetic field activity. Because remember that coronal loops is a manifestations of presence of active regions where magnetic fields are actually active. Okay. So from here, from the active regions and from other parts of the solar corona, we can actually observe two transient energy signatures or transient activities. We call them your solar flares and coronal mass ejections. Okay, but before doing that, let's have a quick review of what, let's have a quick review of about the energy being generated by the sun. Okay, so first is energy generates electromagnetic waves. So this, when you say steady energy radiation, that means this energy in form of or propagated by electromagnetic waves is being given off constantly. That's why it's called energy. Okay. And this is usually depicted in terms of the irradiance or the solar spectrum of the solar radiation. Okay. So more or less, this is constant. Okay. But when there's transient radiation coming from electromagnetic waves, it's a different case. Okay. So all in all, a majority of the spectrum of the solar radiation is in the visible infrared range, with some parts belongs to the ultraviolet and even in X-ray and even in radio wave spectrum. Okay. So aside from electromagnetic waves, we can actually observe particle radiation because of the temperature gradient between the surface of the sun and the interplanetary space. Plasma or material is actually being given is carried by the solar wind. Okay, and this is the reason why if the magnetic dipole of the Earth is actually compressed in the day side and elongated on the night side, thus forming the magnetosphere. Okay, now these two energy radiation can be of transient nature, and when there's a transient nature of this and this steady energy radiation, we call them transient energy radiation. Then that includes solar flares. So that is the transient energy radiation involving electromagnetic radiation, and there is also plasma clouds and high energetic particles. Okay, so these are regions, or these are events that happens relative to the sun on every now and then. Right, that's why it's called transient. It's not always happening. Okay, and in today's class, we're going to focus ourselves with the two most basic or two common transient energy radiation called the solar flares and plasma clouds. And this is these are considered to be transient solar corona activities. Okay, so this is an example. We're going to look at this. Okay, so this is an example of your, if you're going to see a very bright, faint, bright spark at this region, you can see that we call that the solar flare, a very faint solar flare that happened last July 3, 2021. If you're going to look at the corona graph, you can actually see that as that ejection of material. Okay, and then today we're going to look into this. Now, as mentioned before, let's have a quick review. This is the continuum, HMI continuum image of the sun in September 6, 2017. Okay, and there have been identified in the main area of the sun 4 active regions. So you have your active region 2677 and 2678 here. And then these are 2 active regions. This is a AR 2674, and this is AR 2673. Okay, and then if we're going to look at its magnetogram, so we can see that AR 2677 is actually of the alpha characteristic or class. 2678 and 2674 are both beta class. However, 2673 is a very complicated active region. This is a beta, gamma, delta class. It's a very, very complicated. Okay, so that's why. So that's the reason why, because this is a very active region. Okay, so this magnetic classification actually gives you an idea how magnetically active an active region is. Okay, so if we're going to look at the hottest material, okay, about 10 million Kelvin wavelength. Okay, the wavelength that we're going to use, if we're going to take a picture of the sun, 131 angstrom. At 131 angstrom, we can actually observe the height, observe the plasma material at that are at 10 million Kelvin. Okay, so very, very hot, no? So that's why we use this to actually observe solar flare. So this is an example of a solar flare that happened in September 6, 2017. Okay, this is just the peak of the flare, but this is a picture of the flare. And you can see that this region, this very complicated beta, gamma, delta class active region, is the one that produces this very bright emission of the extreme UV radiation. Okay, and this is what a solar flare generally looks like at this wavelength. Okay, so that's why we define solar flares to be localized, explosive release of energy that travels in the speed of light in all directions. So when you say travels in the speed of light, that's because the nature of this event is electromagnetic. Okay, so because electromagnetic waves travel with the speed of light, therefore, solar flares, effect of the solar flare will be released in a speed of light. These are localized, so usually they are associated with active region, and they appear as a sudden, so brief, short-lived brightening of the vicinity of the sunspot. Okay, so if we're going to graph that, that light, it will start to appear at a very sharp increase in electromagnetic radiation, and then relatively gradual decrease in, it's like a flash of light at the surface of the sun. Okay, again, as I mentioned earlier, it usually happens within the vicinity of sunspots in the chromosphere. So it's not happening in the sunspots themselves, but it's actually above the sunspots. Okay, and that actually is related to that usually happens when the magnetic configuration of your active region is a very complicated one. That's why when there are appearances of active regions that are in the complicated scale, beta delta to beta delta gamma to delta, etc. The relative forecasts on the percentage of probability, or the probability of experiencing or producing these active regions of solar flares. Okay, so the probability of producing solar flares within these active regions increases a bit. No? That's why it's very important to observe these active regions and classify them based on their magnetic activity. Okay, because the solar flares travel at the speed of light, therefore, whatever effect it has on Earth, or they have on Earth, it will be experienced in about 8 minutes. Okay, so very immediate, almost immediate yung impact. Okay, that's why it's very important to really forecast this these events. Okay, so this is the picture of the sun at 131 angstrom, September 6, 2017 at about 10:56 UT. So 10:56 UT, that's already 11, that's already 7. So 11 plus 8. So that's 19 local time, 19 local time. So minus 12, that's already 7, around 7 p.m., 6:56 p.m. Okay, so it's already in the night side. So this event happened in the night side of the Earth. This event happened at 7 p.m. Okay, so what does it mean? It means that whatever happens in this event, kung ano nangyari this event ito, the night side of the sun, the night side of the Earth will not be directly affected. Okay, but there may be consequences later on. Okay, but the point is that any effect by the solar flare are actually more experienced by the day side. When you say day side, that's the side of the Earth facing the sun. Okay, so we're going to move forward in time. It's at 11:50. This is 11:12. Okay, and then this is 11:27, 11:24. So we can see that there's a slight decrease in EUV radiation, but when you reach 11:58, you can see that a sudden brightening. Okay, and it peaked at about 12:13. It's so large, okay, that it actually affected the sensors of the camera used in the solar dynamics observatory. Okay, so this manifestation or this signature, this noise are actually particle precipitation. Okay, so the electrons, energetic particles coming that is ejected from this solar flare actually reach the sensors, and it causes this grainy or noisy feature in the image. Okay, so this will tell us that around this time the solar flare has peaked already. And then after this, you can see that the image of the sun becomes a little bit relatively normal again at 12:28 UT, 12:48, and then 12:42 UT. If we're going to look at the animation starting at 12 minutes 0 UT at the same dates, it would look like this. Okay, so this is the solar flare that happened. So you will notice there are two brightening. So that means there are generally two solar flares that happen during this period, during this 24-hour period. Okay, so let me just slow it down to you. Okay, so the first flare, the first very strong flare happened at 9, around 9 UT, 9:13 UT, and then at about 12 UT, there's another one. Okay, and they both came from the same active region. Okay, so this is how do we usually visualize the solar flares. Okay, so let us look at that one more time. So that's the first one. Sorry, it's first one and the second one. Okay, now, okay, so let's look closely dito sa active region na to. So this is your active region 2673. This is a beta, gamma, delta class. Yeah, beta, gamma, delta class active region. Okay, and this is how complicated this active region. No, very very complicated. And this is how, and this is the picture of that solar flare. Okay, so we use the HMI continuum, the magnetogram, and 131 angstrom images to really understand what happens in this active region. Okay. Now, as you will notice here, there's a very, very brightening in the EUV spectrum. But generally, the scientific community devise a what do you call this, classification scheme to classify solar flares depending on the magnitude of their electromagnetic emissions. If this is your EUV, so we use EUV to visualize, okay, to visualize the image of the sun, but we use X-ray to characterize them. Okay, so I mentioned earlier that during this time there were two brightening moments. So the first one is around 9 UT and the second one is about 12 UT. If we're going to look at, and the timing those timing actually correspond if you're going to measure the X-ray flux coming from the sun. Okay, so this is your X-ray flux. So you can see that it is measured in watts per square meter. Okay, the y-axis is the X-ray flux. The horizontal axis is the time from 0 to 24 UT of September. I think this is September 6. Yeah, this is September No, sorry. 0 UT of September 3 until 0 UT of 9:08. So this marker is actually September 6 until this one. Okay. So anyway, as you will notice here, the first brightening at 9 UT is actually found here. So this peak correspond to that first brightening. And then the second peak, a much larger brightening, happens at about 12 UT. Okay. If we're going to classify them based on their X-ray flux, they can be classified in terms of A, B, C, M, and X. So A correspond to flux range at 1 to 8 angstrom wavelength band at watts per square meter, less than 10 to the negative 7. Okay, 10 to the one order higher, 10 to the negative 7 to 10 to the negative 6. That's a B class flare. So basically, A and B is the background X-ray emission of the sun. Okay, increase activity may be considered to be a flare already, but again, we have to observe it together with this picture. But if there is a brightening in the X-ray flux with X-ray flux of about 10 to the negative 6 to 10 to the negative 5 watts per square meter, that's already a C class flare. Higher, one order higher is 10 to the negative 5 to 10 to the negative 4. That's already an M class. That's a major flare already. And an X class is anything above 10 to the negative 4. Okay. The coefficient of that flux, let's say the coefficient of those flux will be added to the classification. So for example, okay, this solar flare, this one is actually X1 class. So that means the magnitude of the X-ray flux is 1 times 10 to the negative 4. And then this one is actually X9. More precisely, that's X9.3 X-ray flux. So that means that's the magnitude of the peak flux range, the peak flux of this solar flare reached to about 9.3 times 10 to the negative 4 angstrom. This specific solar flare is actually the strongest solar flare that happened in the past solar cycle 24. So that range from around 2000, sorry, I think 2009 or 2008 until 2020. No? Within that range of date, solar cycle 24, this event is the strongest one. And it happened during a relatively low solar activity. Okay. So let's have another solar flare event. Let's try to look at the July 3 solar flare event in 2021. This year, a few months ago. This event has during this day there are 1, 2, 3, 4 major flares that happened. The first major flare happened at 2:31 UT. Okay, if we're going to trace it here in this figure, so that's 2:31. So you will notice this brightening. Can you see it? Okay, this brightening happened in 2:35, and this corresponds to this time. So this is actually a C 5.7 flare. So that means that 6.5 as 5.7 times 10 to the negative 7. Tama ba? No. 4, 5, 6 to the negative 6. Tama ba ako? Let's go back one more. Yeah, times 10 to the negative 6. So again, so this is C 5.7 class flare. So that's 5.7 times 10 to the negative 6 watts per square meter. That's the flux energy, or the energy flux at the 1 to 8 angstrom bandpass. No? Okay. So next would be an M class flare that's 717. So if we're going to trace that, so again, this one is the C 5.7, and then this one. Okay, so this is your M class flare, 715. So around this 717. So this correspond to M. This is a M 2.7 class flare. So that's 2.7 times 10 to the negative 5 watts per square meter. The largest of the series it happened at 1429 UT. That's an X 1.59 flare. So that's 1.59 times 10 to the negative 4 watts per square meter. And that happened sometime there, around 1430 UT. Okay. And the last major flare is another M class flare that happened at 1703. So this is an M1 class flare. So that's 1 times 10 to the negative 5 watts per square meter. And it happened at 1703 UT, like this one. Okay. That one. So this is an M class flare. So you will notice here that these four largest flares, solar flares that happened in July 3, 2021, okay, happened at this specific active region. So so that means for one active region, it can produce several flares in a day at different levels, depending on the level of activity that happens in the active region associated with the flare. Okay. On record, this flare is the first. Yeah, this is the first X-class flare. This one. Just go there. Okay. Oh, sorry. Okay, this is the first and so far the only X-class flare that happened in the current solar cycle 25. Okay, but it is expected, no? It is expected that this types of event will increase over time for the next few years because we are about to approach solar maximum. Because solar flares are associated with active regions. So and active regions increase as magnetic field, as solar activity increases. Therefore, the chance of getting this large X class flares increases as number of sunspots and as solar activity increases. Okay, if this is the largest solar flare so far in solar cycle 25, as I mentioned earlier, the X-class flare of 24th of 2017 September is the largest in the solar cycle 24. Okay, now one study by Yashukevich in 2018 related the X-ray flux to UV flux, and you will notice that there is indeed correspondence. Okay, so during X-ray flux, during solar flare, not only do X-ray is being emitted at large quantities, at the same time UV radiation is also emitted, no, in large quantities. So both in the short wavelength and in the long wavelength part of the UV radiation. Okay, so the black part is the 2634 nanometer, and then the green and then the red one is the 0.1 to 50 nanometer wavelength range. Now, aside from UV and X-ray, another important aspect that may happen, not always, doesn't necessarily it always happen, but sometimes a burst of radio waves is also happens. So we call that solar radio bursts. So you notice here that these are two X-class flare. This is your X1 point something X1 flare, and this is your X9.3 flare. Okay, so you notice here that this graph, this is the radio flux in solar flux units. Okay, has been a solar radio burst at this wavelength 1.415 megahertz happened during the, or was emitted or was detected during this flare, this X9.3 flare, not in the the previous X class flare. Okay. Also, it doesn't necessarily mean that solar radio burst only happens during X class flare. There are already recorded observations that solar radio bursts are observed even for lower class solar flares like M class flares or even C class flares. Okay, so this is what we call your solar radio bursts, and this can be observed at different radio waves. Okay, sometimes if you're going to look at solar radio bursts, sometimes you can see what we call your spectrograph, wherein you can actually see detection of several radio wave at several radio wave and certain frequencies, and you can see that certain radio frequencies react differently. Okay, they react differently or were observed differently at different wavelengths depending on the solar flare that happened. This wavelength 1.415 megahertz is a very special wavelength because this is in the L band. So what do we mean by that? This is an L band, so that means the sun emitted L band radio wave, a burst of this wavelength. And how important is frequency? Remember in our physics class, interference happened if at least two waves meet each other in the same medium, okay, with similar frequencies. Okay, so this L band is actually very near to the frequency used in GPS. So your GPS signals, your GPS receivers, let's say in your phones or in your cars, whatever, if solar radio bursts happen, this may interfere. Okay, this may interfere with your L-band receivers in your GPS, which will affect or which may affect the positioning products that your devices provide. Okay, so that's why this is actually very, very important. So aside from producing a large amount of energy, sometimes solar flares produce coronal mass ejections. Okay, so what are coronal mass ejections? Coronal mass ejections are ejections in the solar material into the interplanetary medium. So this is an example of a transient activity in the solar corona that involves plasma material coming from the sun. Okay, it's not electromagnetic. So this is actually, this solar material is actually carried or transferred to the interplanetary medium by an explosion, and then it is carried by, it is produced by an explosion on the solar surface. Sometimes we call them solar storms. And then this material that has been ejected is carried by what we call the solar wind, which we're going to talk about next meeting. Okay, so one of the consequences of a solar flare is that they produce, some of them, not all of them, produce coronal mass ejections. So previously, what we've seen is the solar flare that happened in September 6. Consequently, this also produced a massive coronal mass ejection. Okay, just to give you an idea how coronal mass ejection looks like in a coronagraph. So usually we observe CMEs via coronagraph. Okay, so prior to a CME eruption, you can see that there are helmet streamers. So these are your helmet streamers. And then a helmet streamer is usually visible for a few days. So this is already at around 11:48 UT of September 6. But this, we're going to trace back if you're going to look at this solar streamer, the day before, at September 5, you can see that it's already visible, okay, because of the active region that I previously mentioned. But if a CME starts to erupt, so remember the solar flare happened at around 12 UT. So at 12 UT, you can see that nothing happened because this at this moment the solar flare just erupted. Okay, but remember this is a coronal graph, so this is the sun. So this is your this is your covering. So if there's an explosion, it will still travel from the surface of the sun, or from near the surface of the sun, towards this radii, about 2.5 radii from the about 1.5 solar radii, or 1.5 solar radii. That's why you cannot see the effect here. But as you progress at 12:24, this halpha streamer swells in an initial stage of the ejection. Okay, so again, this is the time that the flare happened. And then after 24 minutes, you can see that the explosion starts to expand. Okay, so here you can see that there are dark cavity that starts to come into view. Okay, this cavity, and then the eruption happens. So let's look at that. So this is the start of the expansion or the explosion, and then the explosion, the material has been ejected already. Okay, so this is now the sequences. So if you're going to look at the movie, you can see that explosion happens. It's not as quick because it's not in real time. This may take minutes, by the way. No, you will notice, no, that the magnetic field, that the solar flare exploded at 12 UT, and this figure, or this last figure, is already 2 hours 36 14:36 UT already. But doesn't mean that solar coronal mass ejection are very slow. No, in fact, they are faster than usual. Okay. Now, there are different kinds of CME. What I showed you is just a CME that are associated with solar flares. But there are different kinds of coronal mass ejection. Another more popular solar flare that can be observed are eruptions of prominences and filaments. Remember in our last class, filaments and prominences are basically the same theme. We're just observing them in different view. If we're going to observe them at the limb side, we call them prominences. Okay, like this one. If we're going to look at it at the surface side, at the main disk, we call them filaments. Okay, so aside from these are the two most common, no, by the way. There's also what we call coronal dimming, Morton waves, and coronal waves, as well as post-eruptive arcades. 2 solar cycles ago, solar cycle 23, a study was made, and they counted how many of this happened during the solar cycle. Okay, and they found out that the coronal mass ejections are best associated with eruptive prominences, or sometimes we call this disappearing filaments. So if your filaments are going to, if we're going to see the filaments, observe CMEs by eruption of filaments or prominences, prominences would look like this. Eruption of prominences will look like this, but filaments will look a little bit different, which I'm going to show you later. No? But anyway, it's about 70% last solar cycle. I'm just not sure now. I haven't seen a paper about the current solar cycle. Okay, so of course, next best associated would be solar flares. Next would be solar flares. However, again, as mentioned earlier, solar flares do not necessarily mean eruption of solar flares. That doesn't necessarily mean production of coronal mass ejection. It's not always the case, but they can be associated with each other. Now, let's look at coronal mass ejection coming from an active region. Okay, so it usually starts. Remember that sunspots usually come in pairs. Okay, so meron kang north and south. That's why I haven't seen a solar flare or even a coronal mass ejection that was ejected from a alpha class. Okay, minimum should be no, no, at least at the very least, the magnetic classification of your active region should be at least beta. Okay, if you increase it further complication, then more complicated magnetic field configuration will appear, and they are more conducive uh, to such events. Okay, so for example, we have a beta class solar active region. So you have your north and south or opposite poles. So magnetic field line would look like this. And then as magnetic field activity increases, so this magnetic field will start to grow like this and like this until such time that we can see that this magnetic field line and this magnetic field line are already opposite to each other. So therefore, they are actually prone to attraction. So once they start to attract, okay, and what a phenomenon called magnetic reconnection happen. Okay, I'm sure you have already encountered that magnetic reconnection. We're not going to mention the physics of magnetic reconnection. It's very complicated. No? But the point is that because this region is filled with plasma, therefore magnetic reconnection can happen. So once that happens, there will become an X point configuration wherein this magnetic field line and this magnetic field line will meet. And at this point, an explosion of energy will happen. So this magnetic field line and this magnetic field line will reconnect like this. This magnetic field line will reconnect to each other. Okay, there's no moment that there will be an open field line. Remember that. Okay, this is a very instantaneous phenomenon. Okay? Okay, it should not violate Maxwell's equation. Okay, but anyway, my point is that once this magnetic reconnection happen, okay, energy will be released at the X points. And that energy is the one that will propel the plasma here away from the sun. And then this magnetic field lines or the plasma within this magnetic field lines will go back towards the sun. Okay, so this explosion happens will involve a large release of energy. Okay, so if we're going to look at the, my go-to animation. So this part would be like this part. And then at this moment, you can see that this magnetic field line, which is going to the left, going to the right, actually starts to be attracted to this magnetic field line, which is going to the right. And then once that magnetic reconnection happens, the energy that is produced during the magnetic reconnection will be one of the responsible forces, so to speak, in the ejection of this solar material. So the solar material is actually trapped within this magnetic field line, which has been discussed using the frozen-in theorem that we discussed a few weeks ago. Okay, so this will be a schematic diagram of a coronal mass ejection produced in an active region. So as I mentioned before, not all coronal mass ejection are produced during active regions. Okay. Now, as I mentioned earlier, coronal mass ejections are observed using the coronal graphs. So these are two kinds of coronal graphs, C2 and C3. So C2 is the more close-up view, and then C3 is the more wide view. So usually we use the C3 to estimate the speed of this coronal mass ejection, which is very important to forecast when, if ever, when it will arrive on Earth, which is very important to us. Now, So for example, but sometimes some coronal mass ejection are not as obvious when looking at, let's say, at C2. So that's why a derivative product has been derived. We call this D2. Okay, and this is derived from C2. This is actually difference between two coronal graphs. Okay, so that it will see more closely the production of your coronal mass. So let's say this is a 325, a 1335. So if you're going to look at 25, sorry, 1325. Okay, so this is the picture of the two. So you will see more clearly the CME. Okay, so how how the plasma cloud actually propagates the sun. Okay, so this is one. Another option, another picture would be this one. So this is a D3. So difference for the C3. Okay. Now, so from here, we can actually generate or estimate the speed of your coronal mass ejection. Typically, the speeds of your ejected material range from about 50 kilometers per second to about 2,000 kilometers per second, sometimes more than that. So it depends on the amount of explosion that happened in the solar corona. So for example, this is that September 6 solar flare. No? So at the left side is the D2 coronal graph, came from C2. The center, you can see the sunlight, the solar surface from a different product. This one is your X-ray flux. So this is the X9.3 solar flare. Okay, so this will be in slow motion. So you will notice here, up. Okay, at this point, at 12 UT, that X class flare happened. That X9.3 happened. And then on the next slide, okay, so you notice that the X-ray flux dimmed because the material has been ejected already. Then you can actually see that explosion that you saw earlier, but this time it's more clear during this time because of the this product. Then you can actually measure these points, and then you can calculate the distance between this point from the center, and then on the next frame you can actually calculate this area to how much it traveled from this point to this from this point to this point at a certain direction. Same goes here, etc. Okay, so by measuring the distance from the center of the sun of some of the edges, as a function of time, we can actually measure or estimate the speed of the coronal mass ejection. Okay, in fact, a simple position versus time graph actually is being used. No, I'm sure you're already familiar with the position versus time graph. No, so this is the position, which is height, and then this is time. So very simple, no? Position versus time graph. And they plotted the positions of the coronal material as a function of time. And then just use the best fit line to estimate the speed. So using the best fit line, the speed is estimated to be 1,571 kilometers per second. So this particular coronal mass ejection, okay, is about 17, on the average, 1,570 kilometers per second, which is a very, very fast coronal mass ejection. Okay, so you notice here that more or less based on the graph that the material moved at fairly constant velocity. Okay, at constant speed at 1,571. Okay, so therefore the acceleration, is almost zero. Okay, it's fairly very minimal. Okay, but there are coronal mass ejections that are actually accelerating. So this is an example of that accelerating coronal mass ejection. So this happened in January 1, okay, the new year of 2020. So when they plotted the position of the coronal mass as a function of time, it looks like this. So you notice that it's not really a linear graph, but using a linear fit, you can actually already estimate the average speed of your mass. And it's about 336 kilometers per second. But you can actually make a second order fit, which there describes that the material is accelerating. So the acceleration of this material is about 8.76 meters per second. But the speed is 336 kilometers per second. So it's a very, very fast magnetic field. It's a very, very fast coronal mass ejection. Okay. Now, lastly, before we continue, one of the last few points, some other characteristics of CMEs. Typically, the mass of CME is about 5 times 10 to the 12 to 5 times 10 to the 13 kilograms. Just to give you a comparison, the mass of the Earth is about 5 times 10 to the 24. So it can be, in fact, it can be several orders lower, but it's still very large in terms of mass. Okay, together with your linear speed and your mass, kinetic energy may range from about 10 to the 23 to 10 to the 24 joules in terms of magnitude. Okay. So again, let's go back to this X-class solar flare. So this is what happens during a solar flare. And as mentioned earlier, a coronal mass ejection is usually happens after a very large X-class flare. Okay, so this is another example. The same flare during the second using a C3 corona graph. Okay, now as I mentioned earlier, not all CMEs come from not all CMEs come from solar flares. There are CMEs that come from filament eruption. So if you could recall, using this 304 angstrom image of the sun, this is an image that can be used to describe your corona. From here, we can actually see several features. We can see your prominences, you can see your corona loops, but more importantly, because remember the filaments and prominences are the same thing. We just name them differently. So this is an example of a filament prominence structure, a very large filament structure. This is another filament. This is another filament. This is another filament. This is another filament. Okay, if you're going to look closely in this filament, you can see that a CME actually emerge here. Okay, again, this is your CME. That is a filament eruption. A CME associated with a filament reaction. Filament eruption. Okay, so the eruption happened at around 1945 UT. So if we're going to look at the corona graph, it will look like this. Okay, so that happened at around 945. So this is the eruption that happened here. Okay. Okay, so this happened in August 31, 2012. Okay. Okay. This is another an example of eruption. This happened in April 28, 2015. This is another filament eruption. So again, we can see a lot of filaments here. There's a large filament here. There's a large filament here. There's a large filament here. Another filament here. Filament. And the one of the biggest of them all is this filaments. And if we're going to play this filament is the one that explodes. Okay, so you notice here, no, the one that the region that left that leave the region that this filament left brightened, and then there's a this bright spots or this bright region actually go sideways in the opposite direction, clearing. And then there's another small eruption happened here, this one. Kita nyo ba? Again, let's play this one. Now you can notice here that the eruption happened at around 224 UT. Now let's look again at the coronal graph. So at around 14 UT, you can see the explosion. Okay, so that's around 14 UT. So we can see that there was an explosion right after 1424. Okay, so this is an example of a filament eruption that happened in April 28, 2015. Okay, so just to compare the sunspot number and the occurrences of CME, they basically follow the same trend. So that means the more active regions there are, the more CMEs that happen. But again, as mentioned earlier, during this period, as described by another paper, not all CMEs come from active regions. But okay, because number of sunspots are proxy parameter to describe solar activity. So that means filaments, eruptive filaments, actually are produced more frequently during solar magnetically with high solar activity years. Okay, and they basically follow a linear trend. Okay. Okay. Last figure. Last event. No. This is last December 7, 2020. So this is an example of what we call a halo CME, wherein the CME that happened, we're going to look at this, that happened in the material that was ejected, or the material in a CME was ejected in all directions. We call that a halo CME. Okay, so this is a halo CME. Okay, so it's not like the earlier examples that majority of the material is only ejected generally in one direction. So this is an example of a halo CME. Okay. And when the speed was determined, it's about 1,400 kilometers per second using your position versus time graph. Okay. Now, as I mentioned earlier, the coronal mass ejection speed, or CME speed, is very important in terms of predicting if this CME will reach the Earth, and if ever it will reach Earth, when it is expected. Typically, CMEs of this kind will arrive at around 2 to 3 days. But of course, it will still depend on the interplanetary condition. That's why scientists have come up with this kind of model. We call this the WSA Enlil model. Okay, So this is an example of a combination. This is an example of a solar wind model. Okay, so in the next topic, in the next class, what we're going to talk about is to how is this way? Okay, bakit ganito ang itsura ng solar wind model? Okay, if we're going to play this is your background solar wind. Okay, this light colored, green, yellow, pink, white, and even black colored. These are regions of high stream of solar wind, maybe due to a window open called a coronal hole. But the point is that this is your background solar wind. Okay, but when this thing happened, one of the main information that we need to look at is the speed of this halo CME. And then when they come up with this speed, this information together with other input parameters, was inputted in this model. And then when they produce this model, they can actually predict to certain level of accuracy that the CME, the plasma cloud that came from the CME will arrive on Earth at about 2 days later. Okay, so it will arrive at around 9 January, December 9. Okay, depicted by this large peak. And it looks something like this now. If we're going to play it, it would look like this. Okay, so this is your cloud. Okay, so this is your cloud. You can see it here. This is the cloud that was modeled coming from your this would be the cloud. Would be the cloud of high speed material propagated from the sun due to this CME. And then we can see that actually this one, you can actually see this here. You can actually see it here. This is plasma density. This is radial velocity. Then we can actually see that this dot is actually the Earth, and it will reach the Earth at this point, at this time. Okay, so this part is actually from the high-speed stream. This part is actually from the CME. So these two peaks is actually a combination of the effect of this high-speed solar wind and your CME. Okay, so you can see it here. This model is actually used to predict, or to guide explorers, outer space explorers, satellites, if and when, for example, let's say a spacecraft that is expected to reach a certain planet at this certain time, and something happens from the sun, they could actually model this to reach to those levels or to those distances, so that they can expect something. They will be able to expect something, an event like this, or they can what I mean is that if a certain satellite reaches the certain distance at this position relative to the sun, they can know whether or not this kind of event will actually hit that spacecraft, which will affect the performance of the spacecraft. Okay, so on this note, what we're going to discuss next in the next video, or the next class, would be the concept of the solar wind. So now we are now moving past the sun, and now we're now entering the region, or the space environment, or the region between the sun and the Earth. Okay. Just to give you an idea, where do I get how do I know if a certain date has a CME or not? You can actually explore this website. This is a catalog of all the CME that was recorded from 1996 to present day. Okay, so this is a catalog of CMEs from 1996 to 2021 up to May. So let's say last May, you can actually see all the CMEs that was recorded You can see the remarks. Okay, you can see if it's poor events. There's a if the CME can be produced by can only observe by a C2. Okay, so let's look at a more recent. Let's say this one. Okay, so poor event, poor event, poor event, poor event. There's a data gap. Let's say partial halo, partial halo, partial halo. This one is a halo. Okay, so let's look at this. We can look at the, okay, so we can open April 8th. Can you see the video? So you can see that there is a CME produced. So ito yung sinasabi ko kanina ang dark area as the CME expands. Okay, so now what you can see here within April 8th, 13. So this is a halo CME. Wait, this one, no? Then you can actually see this is the data. Oh, sorry, this is the CME that we're talking about, not the other way around. No? This is a CME. And then this is the data itself. So height is a function of time. Ito, the first column is linear speed, and then second order linear speed if it's accelerating. So let's go to that halo CME again. So the linear speed is about 513 kilometers per second. So it's a bit, it's actually slowing down. I'm going to look at the graph. No? So it's slowing down. The velocity decreases over time based on the data. Okay, so that's how you can calculate this one. Then you can look at the C3 data. Yung kanina, yun yan. Okay, and then ito, Java movie. Hindi ko alam tsura nito. AIA difference. But anyway, these are some of the additional information. Okay, so that's it. That's our lesson for today. Thank you and have a great lunch. Okay, bye-bye.